this is a very fundamental and measurement. Electrical means we need to measure, we need to flow uh, this current and measure voltage. You can measure any like a capacitance, you can measure power, and we can measure specific heat. So there is a like a plenty of options to measure in electrical transport. But really is not able to, I'm not able to talk all this technique, but I'm so focusing my measurement on electrical, where we flow a current and measure voltage is called a like resistance. So what we do, like a relation between current and voltage. So we flow current and measure the voltage by putting the some contact resistance, by putting the wire, and so that this is a simple thing where we can apply a Ohm's law to calculate the resistance, because we know most of the people who pass out after like a 10 plus, so 10, then we know what is the Ohm's law. Then after applying the Ohm's law, we have resistance. So these two quantity, the very best quantity. We cannot go below these basics. This is the basis of the measurement. We apply electric field in term of a current, and we measure the voltage difference. Then we apply Ohm's law and calculate the resistance. Then after convert into a resistivity, resistance and resistivity, I will tell more detail about them for that. But so as we know, so resistance, so resistivity we can convert into conductivity. Resistance we can convert into resistivity by measuring a, a perfect shape and size of the sample where we need, and we apply current and measure voltage by applying Ohm's law. We read it resistance of any kind of solid material. Either the doesn't matter is magnetic, non-magnetic, insulating, and conducting. Then we have a perfect geometry where we apply a perfect geometry by measuring the length between the probe and area of the cross section of the sample. Then we calculate the resistivity. Resistivity is the intrinsic property of material, where resistance is the extrinsic property. Intrinsic means intrinsic means is that, so doesn't so depend upon geometry of the sample. But resistance is depend upon geometry of the sample. Means here resistance is proportional to this separation between the voltage lead and area of the cross section. But resistivity is independent of the shape and size of the sample. Then finally, we after measuring the resistivity, then we by applying this formula, because conductivity is a tensor quantity, then we have to take the so this diagonal element and even after diagonal element and from the matrix, then we convert resistivity into the conductivity. And similarly, this is the normal conductivity, and similarly here we have Hall conductivity. We measure first Hall voltage, then convert into Hall resistivity, then finally we convert it into Hall conductivity. So these are the standard formula. So if in school time, if we ask like what is the relation between conductivity and resistivity, so normally normal students say which one doesn't know this tensor or quantity, they said so inverse of the resistivity is the conductivity. But that relation is true and without magnetic field. So that relation is true, but this condition is that without magnetic. Why? We can see here this Hall is only developed in presence of magnetic field when we have a non-zero magnetic field. But here, if magnetic field is zero, so this term is square term of xy is like completely zero. Then we have a inverse of the resistivity is called like conductivity in both case, the normal case and in Hall case. Once we have a field, then that relation is not valid. Inverse relation is not valid, then we have to apply a tensor relation, which one is written here. So we can so basically to measure a resistance of the sample, we measure the first apply the current and measure the voltage, then measure by applying the Ohm's law, then measure the resistance. Then by applying the geometry, we measure resistivity, then finally convert into this conductivity by applying the tensor quantity. So how to measure? So there is two methods, and state one two method. One is called two probe, one is called four probe. But normally we measure by four probe, not two probe. So four probe, and we have two method. In four probe itself, we have a two method. One is called linear voltage method, where we put the linear this contact on the sample. Another one is Wonderpow method, where we put this contact on the edge of the sample. So if our sample is a perfect geometry like rectangular or a like rectangular or hall bar, which one is real picture is shown here. So this one we normally measure in linear mode, linear voltage mode, because in water power method, then we have to apply again some geometrical this factor to calculate the resistivity on means of resistance. But linear method is a very popular and straightforward, where we don't need to calculate any geometrical factor, but we need to this calculate the geometry of the sample, where we have length and area of the cross section. So these two are the voltage lead, and these outer are the like a current lead. We flow the current by with the help of a source meter, then measure the voltage difference by a voltmeter. We call a nanovolt. So this one is linear, but in same geometry, when we have a perpendicular to the apply current, we measure the voltage. That's called Hall voltage. So I will talk later this Hall voltage, but in present uh, this slide, I always measure normal resistance. So these are the basic things. But in when we have a system where we can apply a field, where we can change the temperature, so that means we have resistance with the temperature the dependent resistance. Then we have a field dependent resistance, and also when we change like a sample type, we have a variety of sample: magnetic sample, non-magnetic sample. So in Hall, so resistance in Hall we can change N type or P type, where we can expect a linear Hall. So when field so dependent Hall resistance is positive, so we call a hole type. When the slope of field dependent Hall resistivity is negative, we call a N-type. So when sample is non-magnetic, when sample is magnetic, so we don't expect a linear Hall like a first figure. We expect a non-linear Hall. Which one is composed with the two terms? One is ordinary, which is called linear. Another one is anomalous. So this sudden this term is called anomalous. Then it becomes linear Hall, like here. In high field, we expect a ordinary Hall. We call it linear Hall. So once we have a magnetic sample like ferromagnetic sample, then we so that measurement is called anomalous. Anomalous Hall measurement. Uh, so geometry is same. Why we measure a 4 probe to nullify this contact resistance? Because always we measure the difference between the voltage probe. So in a two probe resistance, we include this contact resistance. So that one we can't measure actual resistance of the sample. That contact resistance include inside. But when we apply a four probe method where we can exclude the contact resistance, then we have a intrinsic resistance of the that sample, which one we are interested to measure. So, so that is the major difference between two probe and four probe. So once, like suppose we want to measure, so temperature dependent resistance. So and also temperature by measuring temperature dependent resistance, we can see a plenty of things inside. So and like we can we have metallic or insulating sample. So here is metallic. So this is like here cadmium 3 arsenic is a Dirac semi metal. So topology is, I'm not going to tell about the topology, but this is the one type of metallic Dirac semi metal. And here in the graph there is a plenty of different sample from the same batch. So that means we can also extract this quality of the piece of the sample by measuring the resistance. If we measure a different sample from one batch, then we can say which sample is good. Good quality sample means low residual resistance. Residual resistance means when we see the variation of the resistance of a metal, so we have linear variation with temperature, but ultimately at low temperature it start to saturate. So at low temperature, I will tell you more detailed part of the conclusion, which part is which part is which like phenomena dominating. But here is, I want to say here is the quality of the piece of the sample. So once we have low resistance at low temperature, then that piece is good. And also this triple R, when how much is changing resistance from room temperature to low temperature. So if we have a large change, then we can say that piece of the sample is a good quality or highest quality. Like here in sample number A5, which one is blue, we can see the residual resistance is lowest among the all this is like like 6 7 pieces. And also when you divide the room temperature resistance by this temperature, we have highest value. So this quality of the piece we can also measure by measuring the resistance. So temperature the dependent resistance, we can quantify which piece of the sample is good, which piece of the sample is bad. So when we measure here, I'm again measure a WP2, which one is a wild semi metal. So while session metal, so it doesn't matter which type of the metal is that. But so this overall is metallic behavior. We can see it inset resistance when the resistance is decreased or when temperature is decreased, resistance is decreases. So this up to here 100 or 50 Kelvin resistance is linear. So that linear part is called interaction between electron and phonon. But when we go at low temperature, it start to saturate. So that behavior is fully explained by Black Gaussian formula. We can see here in this term. So rho zero, when we try to fit it all over, so rho zero is the residual resistance at low temperature. That means at zero Kelvin. Up to 0 Kelvin, we have some certain resistance. That one is expected at low temperature. And T square term is called electron-electron interaction. And T5 term is called electron-phonon interaction. But not this first formula is a very standard formula. Everybody knows that structure. But we have another, this depend upon material to material. This type of phenomena is occurring inside. So here we can see in the WPT, we fitted all three formula. One is like electron phonon is catching, one is phonon drag, and one is last one is, so this like combination of both. We can see blue one is the good fit. So we can see P2 is governed by the electron interaction, electron phonon interaction, and even and follow also this phonon drag phenomena. So by seeing this temperature dependent resistivity behavior, we can fit the our level formula and say what type of mechanism is inside is happening inside the material. So if the resistance and if we start to measure further even, so resistance is, I can say resistance is the friction. So, resistance is the friction, like a friction of the resistance of the material. It so it cannot be minus. It can be zero in case of the like superconductivity, but it cannot be minus. So resistance is a friction of the material. So all this and origin is the electron phonon interaction, or we can some cases we can say phonon drag interaction, or and some cases it mix up whole process electron interaction, electron phonon, and electron phonon. So that's this all this kind of this phenomena happening, but this also depend upon material to material. So here when we apply magnetic field, so here in the same resistance we measure here without magnetic field, when apply magnetic field, and it start to become like insulating, not really insulating. This material is not become really insulating. That we call a in normal usual word is called a metal like insulating transition. This metal is not a really insulator, but it behave in such a way this at this nine this Tesla all resistance is going upward when we start this pulling the material. So 90-degree here we apply this current the perpendicular to magnetic field. So that is the direction. So here is the perpendicular current with the and perpendicular to the magnetic field. So it's, by measuring sort of resistance, we can see the behavior how resistance is changing with the presence of magnetic field. So if we fix this temperature like here, so previous one is we fix the field, but here we fix the temperature. Like here is red one is 1.85 Kelvin, which one is showing here. So resistance is almost linear variation with the field. Field is on the x-axis, and we measure resistance. We can see formula, then converted whole data into micro resistance by this formula. So this is the resistance, magnetic field independent resistance. This is zero field resistance and divided by the zero field resistance. So which one is behaved like here? So we can see at low temperature there is a king. So that one I will talk later. But here is we can see a by measuring field dependent resistance, we can measure micro resistance. So all this material which is mentioned here in down is all are very high the micro resistance. So that means these are materially very sensitive to magnetic field. So here we can see millions of the million percentage of micro resistance we can see in 9 Tesla. When you measure in like 70 Tesla, is still is going upward direction. This is not going to saturate anywhere in up to 70 Tesla. So that is the origin. So what is the origin of this micro resistance? Why this material is very sensitive to this magnetic field? Because of these are the semi metal. So semi metal is a combination of hole and electron, where we can expect hole band and electron band. When we see the band structure of all these material, so we can found hole band and electron band. Both are present these together. So the interference of electron and hole when we apply magnetic field, that give rise a huge amount of microresistance. So when you see the relation between how this microresistance relate with their charge carrier and mobility. Mobility is sort of how fast electron is moving inside the material after applying a magnetic. This is the definition of magnetic field. So how fast electron is moving inside material. So we know that conductivity is derived by number of charge carrier and unit of the charge and combination of the mobility. So high conductivity means either we have a high N, this carrier density, or we have high mobility. So all this semi metal which one mentioned here on the top, these are the semi metal where we have a high mobility. We have a high mobility. We can see here this graph is micro resistance versus the conductivity as these two Kelvin. We have like a copper and potassium, which are the good metal, and we can also include aluminum. But that one is good metal, but that metal are not very sensitive in presence of magnetic field. But our metal is also an equivalent uh, so this conductivity, which one is equivalent to this copper or potassium aluminum. But these semimetal are very sensitive to magnetic field. That's why we have huge amount of this magneto resistance. So we can see. So once we have this combination of electron and hole, then we can expect a large amount of magneto resistance. In copper and potassium, only one charge carrier, like electron charge carrier, might be only is the present one type of charge carrier. So we don't expect high magneto resistance. So, and what magnitude is governing this micro resistance? What magnitude? That is mobility. When you see, I plotted a huge amount of material. So, micro resistance versus mobility. Once we have high mobility, like in x-axis, then we can expect a high micro resistance. So, so what is the origin of high mobility? Most of the topological material, like semi-metal, where we can expect a high mobility because of the band, this band crossing, where we can expect a linear dispersion of the band. Linear dispersion means we expect a low effective mass of charge carrier, either hole or electron. So when we expect a low effective mass, so we can expect that due to low effective mass, the charge carrier is moving very fast inside the material, where we can expect like high mobility due to low effective mass. And what is the origin of low effective mass? Is the linear dispersion. So I mean, in the basic structure is that, so band dispersion is measured the mass of the charge carrier. But once we have a very low slope, we can expect a low effective mass. So that means due to topology, we can expect high mobility, where we can expect high value of nitrogen. So, another way, we can also measure surface transport in topological material. We have a very special geometry where we can expect a surface state is conducting, but bulk is insulating. So, how to measure, how to differentiate all this material, topological material or not? So, we can design a such material where we can make a unusual uh, core probe. Here we can see first graph. So we flow current from one point to another point, but we measure a two type of voltage. One is front, one is back side. This is back contact of same piece of the material. One is front contact. We call a lateral. That one we call a hybrid. If material is bulk, like a copper. So this lateral and hybrid is the same value because of the whole this current is going through inside the material. It doesn't matter you are measuring front side or back side of the material. So our top voltage or bottom voltage, everywhere is the resistance is the same. But once we have a topological insulator, so we don't expect this current is going through the inside, and current is going through only the surface. If we measure these two quantity again, then we find that these two quantity are completely different. So here, how much is ordered? We can there once we have surface transport. So vertical resistance means here and here. Here is the highest one, then the lateral, like this one, and hybrid one, back one. So this is the order of the resistance once we have a surface transport. So that means by measuring in a resistance, we can conclude that the material is topological insulator or not. So, so that one we can verify by this path of the current. So resistance is the and measure how much distance we are measuring this. So we depend upon this so distance between the voltage probe. So vertical one is highest because all this vertical means back side and front side, and that's all this current is going through the one side to another side. That means that the current is this traveling a long path, highest path. That's why we have a that resistance is highest value. So and Hall resistivity. So as I said in the beginning, we can measure normal resistance and we can measure also Hall resistance. This that give this type of charge carrier. Our material is N type or P type. But as I said, this material is semi-metal, which one we are measuring. huge amount of resistance and huge amount of mobility. So this resistance is the Hall resistance is not linear. So in the beginning, in the first figure sketch diagram where I said um, Hall resistance is linear, but even though that is true only once we have a single charge carrier. Single charge carrier means single band, either electron or hole. So that we can expect a linear change of the Hall resistance with the field. But in our semi-metal, which one we measure, that is composed with the electron and hole. So if the material contain both type of charge carrier, so that time we don't expect linear Hall. We can expect non-linear Hall, which one is here. So we can see, and even though this vary with the temperature at the up to 100 Kelvin, so the major type of charge carrier is electron, because the slope is the negative. But when you go like above than 100 Kelvin, slope become positive. So major charge carrier is whole type of charge carrier. But these two charge carrier we can by measuring Hall voltage, we can calculate the charge density of the sorry charge carrier density of the material inside, and by mobility. So simplest one is called a single band model, where we have a one type of charge carrier. By applying a simple rule, single band model is slope. You can see we measure Hall resistance by dividing magnetic field. We call a Hall constant. So once we have a slope, Hall constant means a slope. So then we calculate this mobility by applying the Hall constant and divide by the normal resistance. This is the mobility. Then by a Hall this constant, one by Hall constant, and divide by elementary charge, we can calculate the mobility, sorry, the charge carrier density of the material. So by Hall measurement, two quantity straightforward, we can measure Hall and mobility and charge carrier density by applying a simple mm, single band model, which one is simplest formula, and we can calculate by previous graph. We can calculate this mobility. We can see here this red one, and we can also calculate the carrier density. So we can see here 100, 120 or 100 is going to change this type of charge carrier, which one is visible here also. So that one we can measure, but mm, this value is like, looks like overestimated, because in real value is not a only single charge carrier. We have both charge carrier. So like here, for example, which one I was telling here, we can see the band structure of any semi metal. For example, the red one is a valence band, and blue one is a conduction band, where we can see this band is a electron type, this band is a hole type, because mm, uh, this one is like inside the conduction band. So I mean, this metal is not a single charge carrier, not a single band. We have really a multi-band system. So which one we calculated from the previous data simplest formula, which one is not true. That value is like overestimated. So we have a band model, where we can. This is also not a very simple model. So band model means how much band is near to Fermi surface. Here we can see a plenty of band, but we cannot apply a plenty of formula, because a number of variable is going to change. Each band we have a two variable. One is mobility, one is charge carrier. You can see here the simple two band model. Which one is here is N1 and mu1, and N2 and mu1. Simplest one is most simplest one single, but Rather than simplest one, we have a two-band model where we can spec, we can separate how much is whole charge carrier and how much is electron charge carrier at a one temperature. But in previous one, we can calculate only one charge carrier at a particular one temperature. So we calculate the conductivity, Hall Hall conductivity or Hall conductivity or normal conductivity. We apply this formula and where we have a four variable, which one we calculated here by measuring resistance and Hall resistance. We calculate Hall conductivity and apply this formula. Then we have a separation of the hole and electron. This one we call the mobility, where we can see this mobility is going down with temperature. And also we have a charge carrier. So by applying two-band model, at each temperature, we are able to separate how much charge carrier is either hole type or electron type or both. So then this is also not very complicated. We have like a three-band model, we have a four-band model. Band model means how many bands are involved inside the transport. I mean, how many bands are lying around the not around the at the Fermi surface. So that depends upon number of band model. So each band model we have two variable. We cannot go like a like three band model and band model where we have a six variable and eight variable. So that time is not going to fit that curve. So two band model is the simplest model. So that one, as I told previously, by measuring this resistance, we can so design we can design the Fermi surface event. So these are we call up and down in the resistance is called a quantum oscillation. The origin of the quantum oscillation is again a quantum, the purely quantum phenomena. So I'll tell you further what is the origin of this phenomenon. When you see, when we apply a magnetic field, this charge dense, mm, this density of state is going to split into a Landau level. So, and when you increase magnetic field further, this Landau level is going to shift. Then the shifting up now level, we have see the jump in the physical quantity, any type of physical quantity. Then here I showed you physical quantity the resistance, but that physical quantity we can see in when specific heat, in magnetization, in torque measurement. So because all this physical quantity is depend upon how much density of state at the Fermi level. So I can show you again. So here initially, when you show here initially is the this band is like a continuous band. But when we go more field, when you apply magnetic field, these band are splitted into a discrete level. Again, discrete level. That formation of the discrete level is called Landau level. And when you go more magnetic field, so each Landau level is shifting. That means is red and white patches is shifting to the Fermi level. That means you change the density of the state at the Fermi level. So if we change the density of the state at the Fermi level, that means we see the changes in the physical quantity. Here the resistance that that changes it up and down is appearing in the physical quantity. That is the origin of the quantum oscillation. So shifting of the Landau level in presence of in increasing of the magnetic field is the origin of the origin of quantum oscillation. So when we have a like a three-dimensional system, which one I showed you in this resistivity. So this each Fermi surface splitted into form a like concentric tube. Each 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 concentric this tube is a density of a state. So that means the red one is highest density. In between, we have a lower density, then again high density, lower density. When we apply, we increase the magnetic field, the size of the tube increases, is go away from the Fermi surface. This black circle is the Fermi surface. Is going away from surface of Fermi surface. That means it density of state is changing. So, and to observing a quantum oscillation is dependent upon this totaling this total the strength of the magnetic field and scattering time of the electron, scattering length or scattering time, and both are related to each other. So I'm telling here scattering time. So we have a condition to which material we are going to observe this quantum oscillation. So here is the normal angular frequency of the electron. This is scattering time. So this multiplication of these two, once we be higher than the one, higher than the one, like more than 5 or 10, then we can see a oscillation inside. Either this one, or we can change into this relation into mobility and field. These two relations are same, but the variable are different. So this one related to this mobility, scattering time is related to B. So once we have, so like here, either we have a high quality of sample. High quality sample means high mobility, or we have a high field. So there is a limitation of the field. We have a 70 Tesla maximum maximum field in our nearby laboratory, but in particular my lab, we have a like 9 Tesla, this limitation of the 9 Tesla. So to see, observe the quantum oscillation, either we have a high field, which one we don't have, we have 9 Tesla only, but we have a high quality of the sample where we can expect a high mobility. So this multiplication of these two quantity is becoming greater than 1. B is fixed, like maximum 9 Tesla, but these depend upon quality of the sample. Once we have a high quality sample, then we can expect a high mobility. Then this together, this quantity become more than one, then we can expect a quantum oscillation in the material inside. So analyze this quantum oscillation. We have a standard formula which is called a elliptic Cauchy formula. So these are the standard formula where we can calculate effective mass, we can calculate the scattering time, we can calculate the splitting of the like Zeeman splitting inside the material. So and also in spite of these physical quantity, we can design the Fermi surface. We can calculate the radius of the Fermi surface. And when we rotate the magnetic field, we can map the radius of all three directions of the uh, Fermi surface. So really, we can design the Fermi surface by analyzing. And other method is we can also by measuring this oscillation, we can differentiate even which type of and which type of oxidation and what is the origin of this oxidation. But here we have a one device again CD3S2. Then and this is the wild semi-metal, but sorry, this is the Dirac semi-metal, but in presence of magnetic field, it become wild semi-metal. So we have two wild points. Suppose in real and inverse space. So here is the wild point in the bottom and top. When you apply magnetic field, this electron is going through the bulk to surface. That is the path of the electron. Once we have the oscillation in the wild sample, we can see here the zero field means this along the device and we are perpendicular. So we can see after analyzing, we can see here is the two, both are present in the material. This device, this is the like a rectangular device, but when we stop the one facet, here is the not a rectangular device. This one is regular device, but here the triangular device. Once we don't have the top surface, once we don't have a top surface like here top surface, we dismiss by making a rectangular device. So we don't expect this part here, this connection of the part, because we don't have the surface. In this case, we have only one frequency here. So only one frequency here. So here we can see the rectangular device, we have both blue one, but in triangular device we have only one frequency. That means really, and what we assume here to explain the Weiss's metal path of the electron in Weiss's metal, which one is really true? That is the real path of the electron, which one we measure. So other one is like a in Weiss's metal, because we are working at topology by and measuring resistance. I'm telling how much advantage of the so resistance in of material, and how much physics we can deal by measuring resistance only of this material. So one is in a topological insulator, we can differentiate surface and bulk transport. In Waltz metal, where we can differentiate again surface transport by measuring quantum oscillation. Here is we can also do this the chiral anomaly. Chiral anomaly is the transport between two wild points. So once we apply a magnetic field and measure the resistance, so because of the this 2 points, suppose we have a system where charge carrier we have in a such a way to source and sink. So by applying a electric field, magnetic field along, this charge carrier pump from one side to another side, then we can expect a decrease of the resistance. So this formula is here. So that term is maximum because it is dot product. This maximum, this term contribution of this term is maximum only when we have a parallel. Once we have perpendicular, we don't expect the contribution of this term. But once we measure here, so we have a extra term here, generate the extra term, which called like a chiral current. Source of the chiral current is between the pumping between one source to another source, one source to sink. So that is only happen once we have a wild semi-metal. Wild semi-metal means we have a wild point which one act like a source and sink. So here one material. So here we can focus only on the parallel field, which one is zero or nearly zero. So here we can expect a negative microaction. A negative microaction. We can see because of the we pump the charge carrier in presence of magnetic field. So that means we are decreasing the resistance by increasing the this current. There is a one contribution of the this chiral current, which one additional current, which decrease this total of the so resistance, this total resistance in presence of magnetic field. That's why we expect a negative resistance. Once we have positive field in perpendicular, where that term is zero, so that once that term is zero, we have a positive magnetic resistance. That means by measuring even only resistance, that one you can say. So that one I can skip because of time, but we can also measure gravitational anomaly. That means instead of applying a current, this we flow temperature gradient. So that phenomena is called this gravitational anomaly, because thermal is related to mass. But another one, we have a another the kind of material we have like a chiral material, like our hand, the left hand, right hand, and like DNA. So DNA have also the chiral structure, but in inorganic compound we have plenty of chiral compound. So like out of 230 space group, we have 64 like a chiral space group. That means really we have a in our inorganic material we have a chiral material. Why we are interested here? When you search a literature, when you see all these living organs like the RNA, DNA, sugar in the living organ are a right-handedness. Only one-handedness exists in the living organ, but in also a amino acid. But when you synthesize the material inside the laboratory, so we have a 50-50 chance inside the laboratory. But in a living organs, we have only one handedness inside the body. So we are interested here. So why once we start from non-living like our lab material, which one is non-living, in a human like human or animal, why this material is only one handedness? So we selected. Once we are able to find the origin, what is the origin of this handedness, it's like selection of the handedness inside the organism, then we have a like a, something we call a like origin of life. So in sum up means this is very interesting topic for us to do chiral compound to see all these phenomena. So here I'm mentioning one phenomena which is called a quantum geometry. As I said, this material, the chiral material, which one exists into both handedness, left-handedness and right-handedness, and once we suppose we fix a one-handedness and make a device, it's such a device, and measure the resistance of one is left side, one is right side, means one is back side, one is front side. So due to quantum geometry, handedness exists inside the material, we can expect a two type of resistance. So this resistance we can see both are in opposite way. So by measuring same material but in two 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 side, one is left side, one is right side, is giving two type of signal. Either is if we are interested to measure one side like this, and change the material other handedness. Suppose this is the left handedness, and the same geometry. If we change the material to right handedness, then same geometry we can expect so this graph. So either we change the contact left right, or we change the material itself left-handedness right-handedness, then we can expect all these things. So by this one I want to finish my first talk, then we can discuss more further. So here, as I said, in electrical, thermal is also same. Just we need to replace electrical by a temperature gradient, where we call electrical resistance and thermal resistance. In Hall, we call a inertial effect. So means electrical and thermal are both very close, very close phenomena, and measurement geometry is same. Only the difference, instead of current, we apply a thermal gradient, and everything voltage and normal voltage and Hall voltage are contact are same. So for this one, I'd like to thank you again for this one. Now I'm open for any confusion or anything for this talk. Then I can start another one in short break. Manoj, are you here?
Yes, sir. I'm very much here. It was really nice to learn basics of magnetotransport.
So I
So,
stop sharing again, then we can take
yeah,
up.
maybe in 5 minutes we can start the next talk.
So that talk I will give very short because I talk already much. So next talk I'll be maybe half an hour or something.
Yeah, yeah.
So we can. That's why we can discuss here maybe some 10 minutes, 15 minutes, if anyone has any doubt.
Yes, sure. So, at this moment, I would like to ask all the participants to please post all the queries in the chat box so that they can be addressed.
I can say one chat from Bhavna Mahesh. What is the quantum oscillation? Bhavna Mahesh from what I shared already. This quantum oscillation is a quantum phenomena. This is purely quantum phenomena where we apply magnetic field that whatever energy level is there inside the material that is going to again like the quantized in terms of Landau level. So if we increase the magnetic field, that Landau level is shifting because there is a relation between the energy and magnetic field. So shifting of the Landau level, it change physical quantity. Change in the physical quantity is up and down. That is periodic in 1 by B. So oxidation means a periodic oxidation. Periodic oxidation that is originated from the shifting of the Landau level, and again formation of the Landau level is the quantization of the energy in presence of magnetic field. That is the quantum oxidation. Other person, RK Gopal, is asking on increasing of the magnetic field, Landau level shift. Yes. Okay. Yeah. That is the origin. Hmm. Other one person is asking to upload the video today, something day, few days
That is for the organizers, that is for ourselves.
for the organizer. Another question I don't see. If you see some question, then we can discuss.
Yes, new
Otherwise,
questions are coming up, sir. The next question from Bhavna Mahesh. Does quantum oscillation affect superposition and entanglement?
no, there is no superposition and entanglement. So this superposition means I really don't know to how to correlate between superposition and entanglement.
I think
Quantum.
entanglement uh, and superposition mainly they we discussed for photons. Now you can relate if they are reasonable for electrons, maybe.
Hmm. Mm, from up to now, I don't think I can correlate between superposition of photon and electron.
Yes, entanglement, I'm also not too sure, but superposition of electronic wave functions are there, and we see interference of electrons, and out of
That,
that,
that
we see quantum oscillations also, some quantum flex phenomena.
mm,
So, possibly, maybe in some other class, we can also refer this type of interrelated questions. And there is one more from Dr. Chansekhar. Not you, actually.
mm,
We have Dr. Chansekhar Malegaon, I think. Uh, mm, he's saying in our lab, we are synthesizing nanomaterials,
mhm.
ferrites, and glasses. Now he want to
Okay.
synthesize quantum material like quantum dots for qubits. So he's asking for, could you help us in this direction? Can you suggest something so that he can
Mm.
pursue that direction?
Quantum dot for qubit. Hmm. Qubit. Qubit. Qubit is quantum qubit, but itself a quantum dot. It can work is like a qubit. I know there is a one model where we can expect a measure Marana-Fermion, Marana-Fermion, which one is itself a antiparticle. He like a physics point of view. Marana-Fermion is a fermion, which one itself an antiparticle. Well, we can expect all kind of quantization, all kind of this quantization, not only zero and one, where we can see in logic gate, but there we can see all type of quantization. So we can expect in presence of a Marana-Fermion, we are able to quantize all the kind of quantum bits. Means a plenty of quantum bits we can design, not only zero and all kind of 1/3, even 1/2, even all kind of bit we can apply. But how to design from the quantum dot? I don't understand this much, but I can correlate if we have a existence of Marana-Fermion. But existence of Marana Fermion, how Marana Fermion exists, which device Marana Fermion exists. Like in normal material, only we respect electron and hole fermion, but Marana Fermion is itself an antiparticle. That one could exist in between the device like a topological insulator and like superconducting. If we make interface between superconducting, which one is like a Cooper pair. We know origin of superconductivity is the formation of Cooper pair. But when we have a topological insulator where we can filter one spin, so device in between superconducting and topological insulator, we can expect a like existence of Marana fermion. That one I can correlate, but not much much beyond this.
Yeah, so I think we will cover this synthesis of quantum dots using some chemical routes and some other physical routes. In the synthesis module focusing on the synthesis uh, techniques of quantum materials. It is towards the end of the course. So there, I think we will address that how to make quantum dots and how we can realize this. And there are some proposals from quantum dots. We can make qubits. So
Hmm.
maybe those lectures may help in this direction. And directly for you, there is another question. Please explain negative magnetoresistance in materials.
Okay. So negative microresistance. There are two type of material we can consider: magnetic, non-magnetic. If material is magnetic, where we have a spin scattering role inside. So in like ferromagnetic material, we expect a negative microresistance because of suppression of the spin scattering. Suppression of the spin scattering. That suppression happen when we increase the magnetic field. All the spin are aligned one side, ordered. All spin are ordered. That one suppress the scattering. Then we have a negative matrix. That is the origin in the magnetic material. But if material is not magnetic, where we can expect we don't expect a negative matter resistance. For example, non-magnetic material, we have a Lorentz force, normal in basic principle, and Lorentz force give the localize the electron or charge carrier. Then we can expect a increase of the resistance that give the positive micro resistance. We don't expect a negative resistance in non-magnetic material. But in case of while, as I explained, in case of while, where we have a while point that acts as a sink and source of charge carrier. So if we are able to pump the charge carrier from sink to source, source to sink, then we have a additional this current, additional current that is called a chiral current. That additional current give like the decrease of the resistance. Once we decrease the resistance, we increase the field, then value will be negative. So that we call them it's negative micro resistance. We can expect in a non-magnetic material, which is wide. So that is the two things. Two possible explanations are there. Oh, another question is from negative resistivity. Is it same as a superconductivity property? No, 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 no. So negative resistivity. So resistivity cannot be negative. As I said, resistance is a friction. Can be zero only, plus or zero. It it cannot be negative resistance, but micro resistance it can be. Like when you check the formula, so resistance with the field minus resistance without field divided by resistance in zero field. So resistance is decreasing with the field. That is called the micro resistance. Resistance is always positive, but when you measure with the presence of field or increasing or decreasing field, so that means resistance is going down when you apply the formula. So this first term is larger than the sorry, second term is larger than the first term. That value give you uh, negative. So, that's why we call it negative micro resistance, not a negative resistance. Negative resistance cannot be. So another question is magnetic material and conducting material are mostly the same characteristic. Magnetic material and conducting material. Either the conducting property directly to magnetic property of it. No, 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 no. This magnetic property means a role of spin, and electrical and conducting this property is this directed to charge carrier. So if electron spin is acting, this means in each electron, in each electron we have two. One is spin, one is charge. So I mean, which one is dominate? Which one is dominating and when? If spin is dominating, so that is like a spin phenomena. Which one is happening in a magnetic material where charge role of charge is not very high, but still that that conductivity is coming from charge. And non-magnetic material we can expect a domination of the charge, not the domination of the spin. So that's the simple so thinking, simple and basic thinking. We can start, Manoj. So let me share another slide. Let me open first, then we can start. Sorry. See the end one. So second one is here. Hmm.
Sorry. So, sir,
So
shall
second,
we move to
can I start?
the next talk? Yeah.
Second one. Yeah. Okay, let me share. Is visible?
Not yet. Yeah, now it is visible.
Now is perfect.
Now it is
So,
perfect in full screen mode.
so the second talk I want to focus on Hall measurement. Hall measurement, and this story start from the very long, maybe something 150 years back. So, her story of Hall. So, when you see from this discovery of Hall effect from nearly 150 years back up to now, there are several this type of Hall effect been discovered. So, when we combine all type of Hall effect, so that you is going to very interesting. So I'll tell you not very deep because of there is a plenty of Hall effect. Is not possible to go each and every in the each and every type in deep, but I'll give you some sort of mm, flashback of the the discovery. So this that I put a Jew of Hall effect. So in that zoo, we have a different type of effect. So we can see here. So discovery of Hall effect start from 1879, discovered by Hall. And again, in 18 we can see how many 2, 4, 6, 8 up to 8 the type of Hall effect has been discovered. So we can see from 1879 to 2023 total 18 type means total 8 type of Hall effect has been discovered. So this is not a end story. There is much more to going to come in future because of this role of charge and spin. So once we have a charge carrier or suppose electron, we can we have two quantity. One is charge, another one is spin. So this combination of charge and spin up to now and type of material even. So we have eight this type of Hall effect. So this is the this is the basis, this basic of the Hall effect, charge and spin, and we have if we include the material type. Now material we have magnetic and non-magnetic. Magnetic one we know are nickel, copal, something is magnetic material, and aluminum, gold, silver looks like is like a non-magnetic material. So we have a two quantity of from the charge and two type of material exist in nature. But how to change this quantity? We have many parameters to change. We can change electric field, we can change temperature, we can change pressure, we can even change magnetic field. But especially in Hall, we change only magnetic field. We we change magnetic field and measure the voltage. So first, we're going to tell Hall effect. What is the Hall effect? So once we have a piece of material and apply a mm, magnetic field. So that one definition is simple definition is like Hall effect is the production of the magnetic field or generation of the voltage in perpendicular to applied current in the direction. Here, applied current in direction is this way, and we generate a perpendicular voltage in presence of magnetic field. That is called the Hall effect. So in without magnetic field, we don't expect any perpendicular generation of the Hall voltage. So there is a lot of this confusion inside which charge carrier, positive charge carrier, negative charge carrier, electron, hole, which side is going to deflect by 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 or due to Lorentz force. So here we have only one quantity, Lorentz force. Which one is like so deflecting the charge carrier in one direction. So by applying a hundredness rule, if we can this like quantify the direction. But once we fix the current direction, fix the current direction, and where we have a electron is going from left to right, or suppose left to right, then we can expect a deflection electron in front to us, and in same, if we consider same direction of the hole, it's going to opposite. But um, uh, but in same current direction, if we fix that one, is like giving the like a confusion. Hole and electron is going to deflect in same direction. So that one is not a this like a confusion, but this is a like a geometrical effect, and totally like a direction will be dependent. Which and which direction we are considering the motion of charge carrier is either electron or hole, and we know that electron and hole is moving in opposite direction. So due to motion of the opposite direction, we can expect in opposite way r. So if you flow the fix the current direction, we can expect in same direction. Anyway, that is the story. So we have to remember, if you apply that rule, then you can. So this perpendicular voltage, we are and again we have the four probe. So as I said, we have a linear, non-linear. We have a linear. So which one discovered by Hall is just to measure a perpendicular voltage by to the this apply per current in presence of magnetic field. That give you charge type of charge carrier, that will give the mobility, and also charge carrier density. So measuring Hall effect is a very good tools to quantify the charge carrier, and quantify the mobility inside the material. So second one, so as I said, we have a two type of material, magnetic and non-magnetic. As the previous one is completely non-magnetic. Once we have a magnetic, so we don't expect a linear, as I said in first one. We expect a non-linear because of the material inside the material, where we have this Hall is composed by two, ordinary and anomalous. So this sudden jump is called anomalous Hall, because we are measuring Hall. So this resistance is called anomalous Hall, and then it become linear as like this one. So this is the ordinary Hall. So if we measure magnetic material, where we expect a spin alignment, polarization of spin. So simple word is polarization of spin. Due to polarization of spin, we have a two type of contribution. One is from due to spin, and other one is from the charge. Charge one is the linear, but spin one is non-linear. So that is called anomalous Hall when we made the mathematic compound. So we can see here two compound. One is CO3SN2S2. This is sundiide from sundiide family. This is ferromantic, and TC 175 Kelvin. Other one is Hausler, CO2 MnCa. We can speak Hall. You can see here is the anomalous Hall. This is not linear. This is non-linear anomalous. And other one is also we can see an non-linear behavior. So we can quantify how much anomalous Hall resistivity. Then finally we can convert into the conductivity. How much anomalous the conductivity that material finally show. So that is the story of anomalous Hall. The third one is quantum Hall effect. So beginning one is first one is Hall effect is now is going to the quantize. So that this is previous one is simple Hall resistance, but which one Hall resistance we are measuring that is really is going to quantize. So when once we take a two-dimensional system, his condition is that two-dimensional system should be very pure and apply magnetic field. That one is already showed you that graph. But here is that what is happening inside physically, what is happening inside the two-dimensional system. Once each charge carrier is inside, once the charge carrier is inside, that inside this charge carrier is localized. Inside charge carrier, inside the material, charge carrier is localized. So and but one charge carrier present at the edge. So that will travel by skipping the orbit. We call a skipping orbit will travel at the edge. So that means edge is the conducting edge is edge is conducting by um, motion of charge carrier due to skipping of the orbit. But inside the material is insulating. That's why when you see Hall blue curve, we have a some step mm, which one is due to the down level. But when you see the normal resistance is measured inside inside the material where we don't have a resistance. It really it's a zero resistance. So normal resistance is zero, but all resistance is like a quantized. You can see at a high field, maximum field, this value, this value of the resistance is really quantized, E square by H. All these two quantity E and H is a basic quantity. It doesn't change independent of the material. So resistance, once is Hall resistance is quantized in terms of E square by H. So that is called a quantum Hall effect. That is discovered by Linging. So he got also this Nobel Prize by mm, this discovery. So as I said, so that all all geometry, quantum Hall geometry, basically is independent of the material and independent of the geometry. When you destroy the edge, when you destroy this this like deteriorate the edge or squeeze the edge, all these quantities remain the same. It doesn't matter shape and size. All this because all this current is going. This is so this through the edge. So this is the first phenomena where we are able to connect this topology with the this type of material. So it is possible to exist that phenomena in and without presence of magnetic field. Yes, that is called quantum spin Hall effect. For the quantum spin Hall effect, I will tell you later. Quantum spin Hall effect, we don't need magnetic field. That occur quantization without magnetic field. Then, then simple question is what is the source of magnetic field? I will tell you internal spin orbit coupling is the source of the magnetic field. Orbit coupling is the strength which act as a magnetic field, internal magnetic field. So that where spin of the electron is separating, is spin up and spin down, then he is going to quantize. So as I said, this phenomena itself, a quantum anomalous Hall, is independent of the geometry, which is directly related to topology. Topology means that is also topology doesn't matter which type of shape you have inside, like a quantum Hall effect. It doesn't matter how much, which shape of the object or which size of the object you have. So this quantization is always, this Hall conductivity is always E square by H. So that is really when you go to deep even. So when you apply a Gauss-Bobart theorem to calculate a surface integral of the different object, suppose here the different object, and so this is called a Euler characteristic, and G is called a genus. So genus means number of hole is inside the object. By calculating the surface integral, we can calculate the how much number of hole is inside. For example, is where we don't have number of hole, so the value of genus is zero. So these are related to topology. That means each type of object, when we have a different of number of hole, so we can expect a different type of this property. But in one type of, if we fix the number of hole inside the object, that means we can expect a same it's the same property from the object. So that is related to topology, but this is not our interest, but our interest to see further fractionalization quantum Hall. In previous this quantum Hall effect, we apply more and more magnetic field in pure material. So still that step, which one is last step E square bar. So that is going to again this quantize like here. So n is the quantum number in previous one, integer 1, 2, 3, 4, 5 something, and but here is n is also related to p by pq, where the p is the prime number and q is the integer. So and well about it, they are able to observe all this the value of fraction, which is inside which one we can see 2 by 5 is less than 1, and 1 by 3 is also less than 1. So all this phenomena, which one is less than number of n, so that means that level is further going to quantize. We have oxidation, we have this is small bend, that is the uh, that is the, again, evidence of the quantization, that is called fractional, not the integer. Integer one we saw earlier, but later, if the material is pure two-dimensional, we apply high magnetic field. This further Landau level is going to quantize because of the interaction between electron interaction enhanced. So that is going to quantize again Landau level. That Landau level is fractional. That's why it's called fractional algebraic. So they also got the Nobel Prize level later. Now is middle one is a spin Hall effect, where we can expect up to now we consider only charge of the electron. But as I said, we have two quantity of the electron, one is charge, one is spin. Now I'm going to talk about the spin of the role of the spin of the electron. So what happened if you design such a geometry? We just take a gallium arsenide like the thin of the gallium, where we can see the quantum Hall effect. But major meaning is that in in previous case we have independent of the spin, but here to see the spin Hall effect we need to filter the spin of the electron. So here is iron is the magnetic where we are able to filter the spin of the electron. And once we make a device of such a device where put the filter, magnetic filter, we call it magnetic filter or spin filter, then and measure the voltage, same voltage like a hall voltage, then we see a effect of spin, how he spin, and how is this voltage is arising due to effect of spin, how much voltage, that is called a spin hall effect. But further, that spin, that hall is spin voltage is further is going to quantize, that is called quantum spin hall effect. So in 2004, that discovered spin hall effect, and 2007 when we have a topological insulator discovered. So that time quantum spin hall effect discovered. So because of the quantization of spin. So when you see the story of topological Hall effect, uh, this topological material where I said inside material is insulating. This one we can see here. Inside is the insulating, but this outside is on the edge is now conducting. But due to strong spin orbit coupling, as I said, the SOC, orbit coupling, when you apply spin orbit coupling inside the material to design, so we have a separation of the spin. So due to spin momentum locking of the um, charge carrier, spin and momentum lock due to SOC, spin orbit coupling, where we can expect one type of spin, one type of electron, one type of spin is going one direction. Opposite one is going in opposite direction. When you change the spin, that that means we need to change the momentum or like direction of the spin. So that is happening in the topological insulator. So the design this agitated steam material, then measure the spin voltage. They are able to quantize here. We can see there the so different biasing voltage. Here we can see red one is really quantized because of the two spin is propagating to one channel. So that quantization is multiplied by 2 square by h. So that is really voltage is going to quantize in term of E square by h because the two spin is going up and down. So in like two channel, one is from one direction, is the spin up is going, and other one another channel spin the down is going. So due to two spin, so we have a two square by h. Then again we have a quantum anomalous Hall effect. So which one is spin is involved? As I said, first slide, anomalous Hall effect. That anomalous Hall in presence of magnetic element or magnetic compound, that anomalous Hall is going to further quantize. So one example is again topological insulator when you dope a magnetic element. So when you dope magnetic element, so that is going to quantize again. But temperature is very low in Kelvin, but this Hall resistivity is further is going to quantize in terms of E by H. So this is a resistivity. When you convert into the conductivity, is become E square by H. So the resistance is again going to quantize. So that one we already observed. So what is the origin? Origin is that we have a like a Dirac dispersion where electron is going free, freely going, but by applying the by doping the this magnetic element, that is going to break. So that is going to break that is spin and open a gap. So that is become a a, a mam- this magnetic topological insulator where we can expect a one spin contribution of one spin. But that one we can design into a multi-layer. Once we have a single layer, we can expect E square by H. But if we are able to design multi-layer compound, so we can expect a n layer. If we have a n layer of material, so we can expect quantization of n multiplied by E square by H. So such a experiment has been done, has been demonstrated by a group where we can see single layer, double layer, triple layer, five layer, up to five layer, they are able to design and observe this value is multiplied by five in short term of like conductivity. In resistivity, it will be opposite one by five. So this whole contribution. So in our case, as I said, CO3 2, that is the layered material where we can expect each layer is like contributing E square by H. When you divide all this into A square by H, we are also able to reach the value of E square by H. We can see here. So, and last one is again fractional quantum anomalous Hall. Now, anomalous Hall is going to fractionalize. So, which one is in, as we know, twisted bilayer graphene, the design, this twisted MOT has to with the angle of 3.5. So, where the measure, and we see here the fraction 3 by 2 in between the 1 and 2. This is the anomalous one from the one spin, but that one is in between 1 and 2, 1.5. That is the um, anomalous hall is really fractionized. So story is that we have a different type of material and different type of phenomena where from the classical to this quantum. So up to now, I showed you a whole Jew story. So as I said, we have a further chance to discover because of the when you combine the spin and quantum anomalous. To it might be some of the like a spin quantum Hall effect, like a quantum spin Hall effect. We can fractionalize it further into fractional quantum spin Hall effect. So, like here, we have anomalous like a where anomalous is quantization quantum anomalous Hall, we have fractional quantum Hall, but we have a spin quantum Hall is spin Hall, but we have only quantum spin Hall. We don't have fractional quantum spin Hall. So we can expect some phenomena in some material where we can see a fractional or quantum spin Hall effect. So that is the it's called a not a finished story of Hall effect. The story of Hall effect is still going on, and more and more this would be there in near future. So by that slide, I want to thank you for your presence and for your time, Manoj.
Thank you so much, sir. It was really nice to see one, two, three, four, five, six, seven, eight different type of Hall effects. So
Yeah.
normally we consider the very first Hall effect like just to know the type of the semiconducting material, whether it is N type or P type. But since we have long history of Hall effect, uh, it is really nice to see you covered all the different types of Hall effect and nicely connected, chronologically presented, and you also motivate us. Maybe we should work little harder to go for the new material, which where we can see quantized, fractional quantized spin Hall effect, right? So thank you so much, sir. And there are some queries still we can see.
Yeah. So I can see
from
one query from yeah, Rajan Kumar.
yes.
So he's asking something non-linear Hall effect. So non-linear Hall effect is also a anomalous Hall is also a non-linear Hall. But when you go to some more order of voltage, which order you are measuring. So basically, in non-linear terminology, we call a like a second harmonic and third harmonic. We up to now, I showed you a fundamental value, fundamental resistance. But in a same contact and same instrument, we can also measure second harmonic. Means which one frequency we are giving, we are if we are able to measure a double this this corresponding voltage, this corresponding to double frequency. It's called a harmonics. First harmonic, second harmonic, fundamental, same frequency. Second harmonic means double frequency. Third harmonic means like a triple frequency. So that will give you some non-linear effect. That is called non-linear effect in general. Either my matter you are measuring Hall or normal resistance. So more than an anomalous Hall, I can correlate with the non-linear Hall, or we can say non-linear Hall. We can say non-linear effect because that time is that fundamental first harmonic. First harmonic is really non-linear voltage. In fundamental one, which one is follow Ohm's law is linear, but same not the same material in some material. If we are able to measure the second harmonic, that would be non-linear because the origin of non-linear is different than the fundamental. I'm not going to tell you the what is the origin, but is that is called non-linear effect. Hmm.
Yes, sir. So possibly there is one more comment, for the same question. So
Hmm.
simply response to two longitudinal currents in the Hall measurements gives us nonlinear Hall effect, or involvement of AC drive current maybe, but you can generalize.
Both.
There may be some more reasons for nonlinear Hall effect. I think you can address this. I think
Hmm. So simply I can two longitudinal current. Yeah. If we have a multi source of this current, so that this could be like in a, we have a multi charge carrier. As I said, one band model, two band model means a single charge carrier inside the system and double charge carrier. They their movement is like a completely different. Which one is like low effective charge carrier is moving fast than the heavy and heavy charge carrier. That means which one we are measuring. There is two different um, source of the voltage. One is from the fast moving charge carrier, one from the slow moving charge carrier. So that give you like a non-linear effect. So multi-charge carrier also can be a source of the non-linear Hall, as I explained in the multi-charge carrier system. Another one is, I think, involvement of AC-driven current. AC-driven current, how it can be non-linear? If there is no effect of the Joule heating, we don't expect if we have an ideal system. Ideal system means like a one single charge carrier and without this magnesium involved inside. So AC current, I think, doesn't give any non-linearity. So I don't think AC current can give a non-linear effect. What do you think, Manoj?
Not
I don't.
necessarily, yeah, not necessarily. And yeah, this is true. Most of the time, when we have different mobilities or different effective masses, we should see non-linearity in the hall. Uh,
Mhm.
okay. Okay. So, sir, there are no further queries from the participants. And
Mm. Yeah, we
uh,
are.
uh, there is one small request or query from my side.
Mm.
So, I think you are heading a group. It has very nice facilities for growth of the quantum material and characterization. What if some of the participants, someone want to collaborate or work with you? Is there
Mm.
any possibility, or what is the right approach?
Right approach means if we want to make first is the fundamental should be very strong. We want to really do a good science. So if the proposal is excellent, which one, like suppose we ignore something or we forgotten some part of the science. So if someone has like a good proposal, good idea, then we can start immediately because whole group I want to my whole group doing science and we can do. But main thing is the proposal should be strong. That one we can start the machine and we can give this some time. So most of the this cases the proposal is not very strong. Just we need some compound. Why we need the compound and what is this focus of that compound? Why this material is interesting? That would be um, this this question to initiate a proposal. That is the overall main goal to initiate anything like uh, yeah, about something.
Okay, sir. Thank you so much for being so generous and guiding us. And yeah, this is true. Actually, the physics behind the proposal and the material should be strong. That is the most interesting part. Okay, sir. Since there are no more queries, I would like to thank you once again. And uh, we need your copy of the PPT, I think, on the email. And